this, so I am going to replace it by a silicon rectifier. Okay, so this is great. What I know now is that the transformer is indeed a 220 transformer, alright, and not an American type transformer. I know that these, the white wire and the black one you see over there, this one here, are the battery connectors. I also know, by the way, that all the resistors that were connected to the S2C plate are good. In fact, they are good. I measured them all, and the point is, before, when I measured before, I was measuring at some, let's say, unknown point on the S2C plate, and until I found the common, that connector there, which I marked in fact as common. And then I started to get all the right values, which is great. So what do I need to do? I need to fix this battery connector. I need to replace 3 capacitors on top. I need to replace the rectifier. I need to replace this high voltage capacitor down below. And I also need to mount a fuse, because I really want a fuse in this machine, since I'm going to use it as an instrument and not as a display thing. So yeah, there are a few things, and I need to replace the AC power cable. So let's get on with it. Alrighty, I took the original electrolytic, which is a 10 microfarad capacitor, out of its enclosure, let's say, of its cardboard housing. Here it is. And it measures 17 microfarad, which is, well, I would say 60% over its rated value. Alright, I replaced the original electrolytic that was inside that cardboard tube you see over there by a 10 microfarad 450 volts. And it fit rather snugly inside that cardboard tube. In fact, the new one is about 1/3 in size of the original one. Anyway, so you'll notice that at the ends of the capacitor, you'll notice that white blob of stuff. Let me take a pointer and show it to you. So over there, yeah, you see that whitish stuff. That's in fact hot glue. Now I sort of overfilled the cardboard tube a bit at both ends with such a glob, because, for a very simple reason, it allowed me to cheaply and effectively block the capacitor from moving. Okay, so it's really rather solidly wedged. Now I proceeded to unsolder one of the paper capacitors you see over there. Okay, so no, it's not an electrolytic, it's really a paper cap, and the black line is just to indicate on this capacitor where the outside connection is, I would say, for the capacitor, so the outside of the conductive material, whereas the other lead is the inside of the capacitor. Now this one will be the replacement capacitor for the one in that cardboard tube, and as you'll notice, the value is the same, so 47 nanofarad, but it's rated for 630 volts. Alright, I replaced the original selenium rectifier, which you see here, and instead I mounted a diode, a 1N4007 diode. If it wants to focus, come on, focus. Yep. So I mounted a 4007 diode, a 1N4007, on an insulated standoff. Well, actually, it's a nylon standoff, you see there, to which I attached a copper screw to which I soldered my diode, and then I soldered it through to the 1K resistor, which is in series with the cathode. Okay, so a small detail that might be important to note is that if you look on the schematic, you'll notice that next to the cathode of the rectifier, you'll see a small plus symbol. But don't let that plus symbol fool you, okay? Apparently, in the olden days, they used to indicate the cathode of a rectifier or diode with a plus symbol. But it's still connected in this way, okay? So the cathode to the 1K resistor and the anode to the secondary high voltage coil of the transformer. Whenever you're going to use equipment with tubes, it's always a good thing to test the tubes out. And I've got the tube of the RCA multimeter, the 6AL5 tube, inside my meter. I set everything up except the selector switch, which I'm going to put to position 2, because you know this tube has 2 elements, so I need to measure element 1 with the selector switch in position 2, and I need to measure the other element with the selector on 9. Alright, so the first thing we need to do is test it for shorts. So on my Accurate Instruments filament tester, see if it wants to. Okay, I set the test switch to shorts. Alright, so now I switch it on and I look at my shorts indicator, and the indicator is off. Alright, so now the tube, the filament is heating up. You can see the filament inside the tube there. Alright, so we'll give it a few more seconds, and then I'm going to throw the test switch to regular and test the element out. So here we go. Alright, so element 1 of the tube tests good, and at about, I would say, 73, the emissions. So emission wise and short wise, the tube is good. So for the other element, I set the test switch to shorts and I power on. Okay, the filament is glowing again. You can see it down there. So now I look at the shorts indicator. It's off, so no shorts. So now I'm going to throw the test switch to regular again. And the meter says the emissions are a little bit better. I would say somewhere around 75. The 12AU7 is a double triode. The shorts indicator is off, at least for the first element, the first triode inside the tube. So, okay, now I'm going to throw the switch to regular. And the indicator is hovering right around 70, but maybe a little bit less, maybe say 69 or so. The filaments are glowing. I know there's a bit of reflection, but you see the filaments, they glow. Fine, so now we're going to throw the test switch to regular. And let's have a look at what the meter says. Oh yeah, pretty close to what the other element read out. So it's, let's say, a touch under 70. Now, I ordered, and I just received today, a 0.1 microfarad or a 100 nanofarad, 1000 volts capacitor, okay, which is this one here. And this one will replace the capacitor you see there. Now, ironically, I won't replace this one with this one, I mean just naked like this. I will gut this one and then put this one inside of it. Also, I'm going to connect the new capacitor to the old legs of this one, because I had a very close look at it, and if I try to remove the legs as I would usually do from out of the inside of the multimeter, I think I would do more damage than good. So I'm going to reuse the leads of the old capacitor. Alright, I cut the capacitor out of the multimeter, and as you can see it's an 0.1 microfarad, 1000 volts, so WVDC means working voltage DC, and so it's supposed to be 100 nanofarad or 0.1 microfarad. Now have a look at that. It's almost 8.5 times the value marked on the casing. Alright, so I finally managed to gut the capacitor casing. And it's just cardboard, plain cardboard, but I needed in the end to cut it open lengthwise to release it from the actual capacitor, which is this roll here, okay, which is only, well, which is just 2 thin sheets of aluminum wrapped around itself with a very thin layer, I would say, of some sort of plastic foil in between, and it feels greasy and it is incredibly smelly. We're going to put the new capacitor, which is this, inside of the casing of the old one, and then we're going to fill it up with hot glue, and that's it. Alright, and here it is, mounted and closed up with hot glue. And well, aside for the cut on the back, I think no one would be any wiser on what the capacitor inside the tube would be. So it looks suitably authentic and ready to go back into its place down there. I removed two components out of the multimeter, and I'm going to show you which ones. So this one right here, this potentiometer of 500 ohms, and this resistor of 330 ohms, because I'm not confident that they would be good. And in fact, here they are. So that's the AC0 potentiometer. Come on, focus. Yeah. And it's a 500 ohms potentiometer. We're going to have a look inside of it in a minute. And then there is that 330 ohms resistor. Now, obviously I checked the value, so the potentiometer is hooked up to my multimeter, so let's see what it measures. Okay, so touch this. Alright, so there you go. The value is 634 ohms, which is, well, pretty bad. And then you have the 330 ohms resistor. Okay, come on. Right, there you go. So the resistor measures 422 ohms instead of 330. There is still one more part that needs, I would say, restoring, and that's the probe. And here is the result. I just pulled loose the cable out of the connector, and oh, by the way, I did release first a little locking screw in here. Right, so here is the cable. All I think I need to do is to undo the spring on top of it. So let's just do that. There you go. Spring loose, cable free. On to the next thing. Right, now I have to release the coax cable from the main probe. So we do the same thing. We take the soldering gun, we add a little bit of solder to facilitate the heat conduction, like that. There's quite a bit more solder. Okay, give me a moment and I'll show you the result. Alright, I added a little bit more solder and the wire pulled free. So here it is, the probe unsoldered. So I think now what I need to do is to open it up by unscrewing this part here. So that's what we're going to do. There you go. Unsoldered this, and here are the insides of the probe. So now I should find a way of opening it up without breaking anything, so give me another moment to figure it out. Here's a nice family shot for you. So I finally managed to unscrew and disassemble the whole probe, and in fact it's a little bit harder than I thought it would be. So on top of the probe, right over this needle, in fact, there is this little holder here, and it's brass with a little I would say spring on top, okay, and the whole thing screws down over the needle and along this stem here, which has a certain threading, which is not normal metric threading or anything like that. It's quite a wide threading. In any case, as you can tell, there's quite a bit of threading here, so you have to unscrew it quite a bit. I did release this screw, let's say, or this hollow nut with a duckbill plier, so as not to leave any markings on it. And I'm sure you'll notice it has flat sides, so exactly for that purpose, so to grip it with pliers. And then once this was loose, I managed to pull loose the whole mechanism, so this here, and the needle and the soldered resistor out of the case. Okay, it just popped out, as it were, but I had to do quite a bit of pulling to get it out. But there you have it. It's out of it. Right, to reassemble the probe will take a little bit of handiness. So you need to do it in a particular order, and the order is this. So first of all, you need to, if needed, you need to replace the original resistor, the 1 meg resistor, and it's a 1/4 watt resistor, and you need to solder it to the very tip end of the measuring probe, right there. Let me show you in a close-up. So right here, okay, right there. And you need to take care not to put any solder on the sides or anything, just right where you see the end of the resistor. Okay, so once you've done that, you slide on the switch of the probe over the resistor gently and over the stem of the probe's tip, taking care that the opening of the switch is to the top end, to the back end really, of the probe tip. Okay, the next thing you need to do is you take the body, the front part of the probe, and you slide the whole assembly in it until the tip exits on the front end, like that. And you pull it through gently, but in such a way that the switch comes through this opening here, and that takes a little bit of work. So I found the best way to achieve that is to slide it over and then guide it with a little piece of plastic like this, which is part of a credit card. So you slide it like this into the probe, like that, and then you use the tiny sliver of plastic to guide the switch almost to the opening. There it is. right? And with a little push and a bit of luck, it's in. Okay, you pull out the piece of plastic. The next thing you do is, with some tweezers, you take the tiny little washer here. Okay. You take a tiny little washer, you make sure it's clean, that nothing clings to it or anything. Alright? And you slide it over the tip like this. And the washer should drop right into the front part of the probe. There is a small opening into which the washer will just about fit. So, here you go. Okay, there it is. So, the washer is at the bottom. I know it's kind of hard to see, but see if we can zoom in and you can see it, but come on, focus. There. And you can just about see it at the bottom of the measurement pin. Alright, so that's the next step. And then what you do is you take the plastic front end of the probe, you slide it over the whole tip like this. You take the spring, you slide it over the tip, and you take the front end screw, hollow screw. You slide it over the tip like this, and inside the spring. So you need to make the spring slide over it. Alright, like that. Right, the spring is, oh come on, maybe I can do it like this. It's a little bit easier that way. Okay, so you slide it over. Once you hit the thread on top of the tip, you start to screw gently. Yeah, do not force it in any sort of way, just screw it gently in. Now this is a little bit tricky. The screw needs to fit through an opening inside this plastic tip, and if you hit it just right, you can screw it all the way in. Test the slider of the switch if it still moves freely. It does. So now comes the interesting part. We need to install the switch's contact end, the business end of the switch actually. And how you do that is, inside there's the resistor, and the resistor fits through that fat opening you see here. Now you'll also notice on this piece, 3 little cutouts. Remember those little tabs I showed you inside the probe? These need to fit inside these little cutouts. These are the remnants of the AC0 potentiometer, and I'm talking about the potentiometer you see here. Alright, it's a 500 ohm potentiometer, and I also show the 330 ohms resistor, carbon resistor, that was attached to it. So these two parts in effect, well, these 5 parts, let's say, because I disassembled the potentiometer. It was bad anyhow. I mean, the mechanism was really rough and intermittent, and I really wanted to have a look inside at what its state is. And it's actually, well, surprisingly good, considering the fact that it's something like 57 years old. But it's just out of spec. It measures 625 ohms end to end, whereas of course the schematic calls for 500 ohm potentiometer. So its value was off anyhow, and the mechanism was shaky, and I just didn't like it. So I took it out, and I also took out the 330 ohms resistor, which is a carbon type resistor, and this one measures 427 ohms. So that is seriously out of spec as well. I replaced the 330 ohms resistor with a metal film one, which you see sticking out there, out of the bottom. And I'm using a modern little pot of 470 ohms, which is pretty close to what is called for. It's only 30 ohms lower or so. It dawned on me that instead of using all sorts of products and tapes and glues and what name you, there was a far easier solution and much more effective solution available to me. I just used a washer, a rubber washer or grommet, like I used down here. Okay, so this is the grommet for the electrical wire down in the chassis, and this is the same kind of grommet. And I simply looked for a grommet into which the trimmer would fit and would sit snugly so that it didn't move and would not make contact with the metal of the chassis, and there's the result. Pretty neat, eh? And no, it doesn't make contact at the back either. Let me show you. See if I can give you a little bit more light. There you go. Alright, so it's really safe and snug. So about that executive decision I took about the battery. After long and hard soul searching, I thought to myself, well, you know, batteries are really not very good for the environment, that's one thing. Also, batteries can leak, and they often wreak havoc with any sort of appliance. I also thought that why use a battery if I can make something far better to replace the battery. So what I'm going to try to make is a very small power supply, a very small regulated power supply that I will build into my multimeter. Alright, so I'm getting ready to calibrate my multimeter, and I've attached it to my orange connector block over there, which in turn is connected to my variac over there. Alright, so just to be sure that I can control every step of the testing and calibrating the multimeter, you'll notice one thing. Okay, I'll go over everything I did to the multimeter, but there's one little addition to it, and that's the little thing you see over there with a little heat resistant mica plaque on top. Now, I the idea, come on focus, I stepped off the idea of using a battery to do all the measurements with my multimeter. Instead, I built a small reference voltage power supply which feeds off the power supply for the filaments of the tubes. And I'm measuring right now the AC voltage that the power supply, well, the transformer is supplying to the filaments. And as you can see, the voltage is close to 6 volts. It's at the moment it's 5.83 volts, 82 volts. The AC that I pump in varies a little bit, and since it's still only 6 p.m., many people are switching on all sorts of appliances in the neighborhood, and therefore the AC does jump around a bit. You know, it can easily go from 220 to 235 or so. Right now I'm feeding in 200, let's see if I can show you without too much reflection. Right now I set my variac to start with at 224, and already it's going up to 226. Alright, so like I said, the voltage jumps around quite a bit. To calibrate my little reference voltage power supply, I start by letting the voltmeter heat up for say 10 minutes, 15 minutes. You don't need to wait for much longer than that, although the service manual does talk about letting it heat up for half an hour or so, but I guess 10 to 15 minutes is ample. So what I do next is I hook up my voltmeter in DC position to the reference power supply output there. Okay, so mind you, it is also connected to the multimeter, so we're not measuring true open voltage, we're measuring DC voltage, while the reference power supply is already supplying to the multimeter. So that's the first step you need to take. Once all that is hooked up correctly, you take a small screwdriver, like this one here, and you set the voltage as closely as possible to 1.5 volts. Now, that is crucial. Yeah, you need to get it as closely as possible to 1.5 volts, because if you don't, and you will calibrate the multimeter afterwards, the calibration will be off by a few meter ticks, and you want obviously the meter to be as accurate as possible. So I'm very, very close to 1.5 volts, as you can tell. Okay, so we did that. So now let's have a look at the meter reading at the front. So the reference resistance is still hooked up. I'm curious to see what the meter says now. Alright, so let me just do a quick check of the DC measurement. Okay, it's a little bit too high, so let's drop back the DC 0 setting there. Okay, then the setting here is at 1 times R. So now we set the function switch to ohms, and we check the deflection of the scale, and it's a bit too high. So using the ohms potentiometer, we set the deflection at right at the end, the very last tick, right before the infinity symbol, so right here. Okay, and we're pretty nearly there. Okay, so now we set the range to 1000, since we're measuring a resistance of 9810 ohms. So we should get a deflection of 9.8. And no, we don't. We get a deflection of 9.5. So what that means is that the meter needs a little bit of a calibration. So let's do that next.